Prove that S3 comma composition is a group. Is it abelian? Under the operation that is composition. So what is S3? S3 is a symmetric group having 3 elements. That is, S3 has 3 factorial elements. So how will you get 3 factorial? Because S3 contains the elements that is 1, 2, 3. So these 3 elements can be arranged in 3p3 ways. So what is 3p3? 3p3 is equal to 3 factorial. So that is why S3 contains 3 factorial elements. That is, S3 contains a total 6 elements. So these elements can be taken as F1, F2, F3, F4, F5, F6. What is F1, what is F2, F3, etc. So actual meaning is this codomain contains the elements that is 1, 2, 3. And this domain that is equal to, that is also 1, 2, 3. So first one, that is 1 goes to 2. 1 goes to 1, 2 goes to 2, 3 goes to 3. That means 1 goes to 1. The image of 1 is 1, image of 1 is 2, image of 1 is 3. So 1 goes to 1 and 2 goes to 2, 3 goes to 3. The second one is 1 goes to 2, 2 goes to 3, 3 goes to 1. So that means the arrangements of these 3 elements, So that is next one, F3 is equal to 1, 2, 3, 1 goes to 3, then 2 goes to 1 and 3 goes to 2. In this similar way, we can write F4, F5 and F6. F5 and F6. So that is F6 is equal to 1, 2, 3, or 1 goes to 2 and 2 goes to 1 and 3 goes to 3. So these are the 6 elements. So don't change this order. Then we can use the Cayley table. What is Cayley table? So this is the Cayley table. We can use that Cayley table multiplication. So how will you multiply this one? That is F1 into F1. So how will you find F1 into F1? If you take F1, so that is 1, 2, 3, then 1, 2, 3, take that is 1, 2, 3, 1, 2, 3. That means, first you write the image that is as 1, 2, 3, not image, that is the elements for the image. Now 1 goes to 1 and here 1 goes to 1, its value is equal to 1. 2 goes to 2 here, then this 2 goes to 2, that is equal to 2. Then 3 goes to 3 and 3 goes to 3, that is equal to 3. So this is the multiplication way. So in this way, we can get F1 into F1, F1 into F1, that is equal to F1. That means F1 composition of F1. Then F1 composition of F2, F1 composition of F3, F1 composition of F4 and F5, F6. Since this F1 is the identity function, we can get the same value because A star B is equal to B star A is equal to B, or A star E is equal to E star. So this is the definition for identity. A star E is equal to E star A is equal to A only. So E is the identity element. Here identity element is the F1 because what is identity map? So identity map is equal to F of X is equal to X only. Identity map is called F of X is equal to X. Then when you put 1, its image is equal to 1 only. When you put X is equal to 2, its image is equal to 2 only. And for 3, 3 only. So 1 goes to 1, 2 goes to 2, 3 goes to 3. So this is the identity map. So this F1 is the identity map. So whenever you operate with this F1, you can get the same element. That is why, so F2 composition F3 is equal to Here 1 goes to 2, that is 1 goes to 2. Then you take from the second one, that is 2 goes to 1. That implies by transitive condition 1 goes to 1. Now second one 2 goes to 3. Then second one 2 goes to 1. Sorry, 3 goes to 2. That is here ending point that you take from the second as starting point. Now A related to B and B related to C implies A related to C. That implies 2 goes to 2. Now third one 3 goes to 1. 3 goes to 1. Then this ending point is 1. That one you take from the second one. 1 goes to 3. So you can take the answer 3 goes to 3. Therefore, the answer is, first you write the values 1 to 3. Now you write the corresponding values. 1 goes to 1. So this is 1. Then 2 goes to 2. Then 3 goes to 3. So in this way, we can find the F2 composition F3. Similarly, we can find all the compositions by using these techniques. So in the similar way, we can fill this column. That is total 36 elements. And the main thing is, there is no repetition. There is no repetition of elements in each row. See here, first one F1, F2, F3, F4, F5, F6. There is no element repeated. Then second one F2, F3, F1, F5, F6, F4. Also F3, F1, F2, F6, F4, F5. So similar case, in each row there will be no repetition of elements. That is the important one. Now what is our aim? Our aim is to prove this S3. That is equal to this set. That is, this set is a group. So for group we have to show total 4 conditions, and for abelian we have to prove total 5 conditions. So what is the first condition? So the first condition is closure. First condition is closure. What is closure? How will you verify the closure property? You take the table. What is the table? This table contains all the elements of this table. All the elements of this table belongs to the given set S3. That is, each row we can get F1, F2, F3, etc., F6. So there is no new elements other than these S3 elements. Therefore, closure property is true. So how will you write that one? Every elements in the table are belongs to S3. Then that is closure. Then now second is associative. What is associative? That is F1 composition of some F2, composition of some F3. So this is example only. That is equal to F1 composition F2, composition F3. So here you can directly write associative property is always true. Always true in S3 comma composition. Don't need to verify it. So associative is always true in S3 comma composition. Now identity. Identity already I explained. Third one is identity. What is identity? We have the identity element is what? S1, not S1, F1. 1, 2, 3. That is 1 goes to 1, 2 goes to 2, 3 goes to 3. And now fourth one, inverse. So what is inverse? So how will you find the inverse? That is, from the table, you take the each row of this table, each row. So that is the first row. Here F1. First row, F1 is the identity. Then second one, third element, that is this is the identity, that is F1. Then third one here, this is F1. Then fourth, this is F1. Then fifth, here F1. Then sixth, that is F1. So each row we have the identity. Now, first one, you take the first element, we have to find the identity, the inverse element of F1. Then you take the corresponding column which contains F1. So this is the column which contains F1. Its corresponding value, that only the inverse. So inverse of F1 is equal to F1. Always the inverse of identity element is that itself only. So inverse of F1 is equal to F1. So inverse of F1 equal to F1. Now inverse of F2 is equal to. So that is inverse of F2. This is the F3. This F3 column, the inverse, the identity element is F1 here. So its corresponding value is equal to F3. Therefore, inverse of F2 is equal to this F3. So inverse of F2 is F3. Then inverse of F3 is equal to F2. And inverse of F4 is equal to F4. And inverse of F5 is equal to F5. And inverse of F6 is equal to F6. So it is easy way. This is in the first column. Therefore, answer is F1. Then third column for F2, that is F3. Then the third one, it is in this F1 is in the second column, that is F2. Then F4, that is in the fourth column. And the F5, that is in the fifth column. And F6, that is in the sixth column. So we can prove that for each element has its inverse. Therefore, so in this way, we can write the inverse of F1 is equal to F1, F2 is equal to F3, inverse of F3 is equal to F2, F4 is equal to F4, inverse of F5 is equal to F5, and inverse of F6 is equal to F6. So this you should write for this answer. So therefore S3 comma composition is a group. Now to check whether it is abelian or not. For that also we can use this table, that is, you take F3, F5. What is F3? F3 to fifth column. F3 to fifth column. That is, F3, F5 is equal to F4. F3, F5 is equal to F4. So F3, F5 is equal to F3 composition, F5 is equal to F4. And what is F5 composition F3? F5 composition F3. F5 F5 composition F3, third value, that is equal to F6. F6. Therefore, F3 composition F5 not equal to F5 composition F3. For if for at least one element not obey the commutative rule, the given group is not abelian. Here only this is the one counter example for non-abelian. So F3 and F5 are not commutative. Therefore, the given group is not abelian. So actually, what is F1 composition F2? F1 composition F2. That means F1 composition F2 of 1 means F1 of F2